very much, Susan, and also thank you all for joining us, especially the hundreds of people who come back consistently month after month for these webinars. We really appreciate that very much. Today's webinar, as Susan mentioned, proper boiler operation boils down to safety. You know, it's a program I've been wanting to put on or put together for a long time. As there's so many people, so many questions that have been asked of me over the years during various seminars that I've put on or webinars concerning not just inquiries regarding proper boiler operating procedures, but, you know, explain to me, Steve, what these boiler safeties really are, how they work, and probably most importantly, how do I know that they're working at all? You know, this is certainly a very important concern and an excellent question, because boilers, though they're wonderful machines capable of performing really countless heating and process services for us, you know, involving various commercial and industrial applications, they're really, if you think about it and cut to the chase, they're controlled bombs, which need to be respected. They've got to be properly operated, and they've got to be understood in order to be able to provide reliable, efficient, and of course safe operation for many, many years. So, you know, with these thoughts in mind, this is what our program will consist of today. First of all, understanding boiler safety and the consequences incurred when given a lack of understanding and sound operational procedures and standards. And then we'll also briefly review what areas on the boiler should be closely looked at when it's offline and drained either for inspection or maybe it's down for repair. And then we'll spend the majority and the balance of our time looking at the boiler safeties. We'll look at their function, how they operate, and how they're checked before we go into the final summary, as we normally do, and then, of course, the Q&A. When referring to a lack of understanding and sound operational procedures, the consequences actually fall into these two main categories: fireside occurrences and waterside occurrences. Now, as far as fireside is concerned, we, of course, are talking about what goes on with the combustion in the furnace of a boiler after the burner has mixed the fuel and air together and then ignited it. Referring to the formula now on the screen in the lower right corner, you see combustion involves the volatilizing of carbon, and to do this, we need the proper amount of oxygen and an ignition source resulting in carbon dioxide and water, especially with gaseous fuels such as propane, which is shown in the example, and then natural gas, because of all the hydrogen involved with these fuels. Now, what's also evident on the screen is that if you have too little oxygen, we can go fuel-rich, producing not only a bit of carbon dioxide, but carbon monoxide, and a goodly amount of hydrocarbon or particulate, also we refer to it as soot. Now, this is a very dangerous mixture, resulting in some combustion rumble, vibration, before the uncontrolled mix pockets and finds an ignition source, such as glowing refractory, and explodes violently, as shown here. Now, in this particular case, we have a 500 horsepower Firetube boiler, which was burning natural gas, and the fuel-air ratio went extremely rich on the fuel side, exploding in the furnace, blowing off the burner, and sending it on a violent path through walls and equipment. Now, miraculously and fortunately, no one was hurt, but severe damage was incurred within the building, including busted down walls, broken windows, just from the concussive force. Now, that's what we refer to as a fireside explosion. The other very dangerous situation is a waterside occurrence or explosion, which requires a basic understanding of thermodynamics and physics. And to briefly apprise you of this, I'm going to refer you to an actual incident report put together by the American Society of Power Engineers, who, in my humble opinion, are extremely credible because They not only understand the engineering and chemical theory, they live it every day, operating or managing these boilers for a living. Essentially, what is being said on this slide is if you take water, in this case a cubic inch, at sea level, and apply sensible BTUs to it, the water will boil at 212 degrees Fahrenheit. Now, if you then enclose the vessel and continue to apply the heat, or BTUs, what we refer to as we're applying latent energy at this point, the water changes state, goes through a phase change, and becomes steam. And the steam volume, remember it's still a cubic inch of water, but the steam volume when it goes and changes phase increases 16 times at the same temperature. That's what we call saturated steam. Now, the next thing we need to understand and appreciate is the concept of flash steam, or the amount of energy expended when the saturated liquid in the boiler is released to a lower pressure. And to do this, we need to apply the formula shown on the screen at the bottom, which is the number of BTUs at the highest pressure, which is HF1, minus the BTUs found at the lower pressure, which is HF2, and then divide by the total enthalpy, or the total BTUs, both sensible and latent at this lowest pressure. This then gives us the amount of flash steam, which in this example you can see is about 15%. So as you can see in this power engineer example, if we have a boiler with 1,000 gallons of water, and it's saturated at 100 psi-G, which is equivalent to 338 degrees Fahrenheit, pretty hot stuff. And if the vessel ruptures for any reason, a portion of that water, 15% in this case, will go to atmosphere and it will flash. So I've got 15% of 1,000 gallons, that's 150 gallons. 1 gallon of water is 231 cubic inches. So 150 times 231, I've got 34,650 cubic inches of water that's released. Now, since it immediately flashes to steam, the volume of the steam created is 1,600 times, so I've got 54,440,000 cubic inches. Now, 1 cubic foot is 1,728 cubic inches. If I go through the conversion, I've got 55,440,000 divided by 1,728, so I've got 32,083 cubic feet of steam that will be produced. We've got a boiler room that's 10 feet high by 20 feet long and 20 feet deep. It's 4,000 cubic feet. I'm releasing 32,083 cubic feet into 4,000. Okay? I'm putting 8 pounds into a 1 pound sack. I've increased the volume by 8 times. So, in essence, what I've done here, it all boils down to the building structure is overpressurized by 8 times, and the weakest structural components will unbuckle, hurling severe destruction and possible death in its devastating wake. And that includes the boiler and its components as well. Now, here you see a continuing of the Power Engineers report that I've been citing, and showing a manufacturing facility in Paris, Tennessee, which encountered this very situation in 2007. Note the blown out walls and windows and the rear door, which landed several hundred feet away. The one here in the gully in the foreground. You know what? It weighs 6,000 pounds, 3 tons. Looking more closely at the devastation, you see one of the boilers is missing, but the second boiler is still on its pad as it was not the one that exploded. That's the deaerator to the boiler's left, which is also in place. But remember, these are very, very heavy pieces of equipment. Now here's another shot from the inside and showing the deaerator from a different angle, and that wall that's blown out there was primarily caused by that 6,000 pound door which exited through it. Now for the boiler that experienced the Waterside explosion. It traveled several hundred feet inside the building through walls and machinery before coming to rest. And as mentioned, boilers are very heavy objects. And this boiler weighs about 60,000 pounds. You know, it's the same as a fully armed and fueled fighter jet, which is launched by a steam catapult, slingshotting from 0 to 195 miles an hour in 2 seconds, similar to launching this boiler. Now, a short while after the occurrence, a thorough investigation followed, and it was determined that the following were the causal factors: lack of standard operator training, inadequate boiler operating procedures, inadequate boiler attendance, not very good maintenance, and inoperative boiler controls and safety device. Now, the last point, inoperative boiler controls and safety device, meant that the primary and auxiliary low water cutoffs failed, allowing the water level in the boiler to drop to a point where the very hot surfaces were exposed without any way of taking this heat away. And when the feed water pump was eventually energized, relatively cold water compared with the hot surfaces entered the unit, causing the metal to contract and break from its welds. This then bagged the furnace and allowed the water still in the unit to flash off and expand 1,600 times. So, how do we avoid a similar situation in our plant? Well, follow these points. And remember, this can happen with a 30-gallon water heater. It doesn't have to be a high-pressure steam boiler. Water is water. Physics is physics, and heat is heat. It makes no difference the design of the unit. They'll all launch if saturated water under pressure is released to atmosphere. And you know, when you cut to the chase again, most, if not all of these incidences boil down to and could have been avoided with proper knowledge on the part of the operating personnel and their supervisors. The boiler too often is taken for granted with little thought given to the dangers which lurk within it if it is not properly understood, operated, and maintained. And quite frankly, this is unacceptable, as there are numerous classes offered at various facilities throughout the country, such as our CB Boiler House, and including specially tailored on-site training programs addressing specific companies' needs, their equipment, and what they're really truly looking for in terms of improving reliability and safety. And the other thing one needs to understand, and relating to training awareness, is boilers are large consumers of energy and represent a significant share of the cost of operations spent when considering fuel cost alone, saying nothing about the cost for parts and service, especially if the service is on demand and not planned. For instance, on average, a boiler consumes 4 times its original cost in fuel every year it operates. Knowledge and appreciation of this fact should prompt the operating personnel and management to take every avenue they can to mitigate waste and reduce this expense. It's certainly possible, but knowledge is required to initiate and execute what needs to happen for this to be a case. And the other thing that can significantly add to the cost of boiler operation is downtime, which goes beyond the cost of parts and service. For instance, what about the lost production time and possibly the lost product? Or maybe we've got complaints from tenants when the heat goes off on a cold winter day. That's why whenever the boiler is down and drained for inspection or repair, it's an excellent time to look after those things you have noticed when the boiler was running and were so documented. Or the things you discovered during the boiler walk-around and the internal inspection. Things like that handhole gasket that you noted was weeping. and spewing what appeared to be steam, but it's actually condensate. And as time went on, more and more condensate was coming from it. It's time for a new gasket before the situation deteriorates, meaning not just needless energy loss, but possible downtime too if the hole needs to be repaired to allow for proper sealing of the plate. And then there's the water side of the boiler, to see if there's evidence of scaling or possible oxygen pitting, which leads to energy loss, and again, possible downtime if the tubes fail and then the boiler starts to leak. Maybe it's time to have a good heart-to-heart with your chemical treatment professional or operating personnel to assure proper chemicals are in place, the dosing is right, and they're being regularly and properly applied on a consistent basis. We also have the fire side of the tubes, checking to see if there is heavy sooting, which indicates the burner is firing rich, meaning this is not only dangerous, but another energy waster too, because of the insulating factor of the soot blocking good heat transfer. And while we're looking at the fire side of these tubes, let's make sure you inspect the tube attachments and the ligaments between the tubes for evidence of separation or cracking. The tube attachment on a Firetube boiler, for instance, has to be firmly touching the tube sheet, as this forms the heat sink, allowing the heat transfer through the sheet and into the water back surface behind. Now, failure to give up this intense heat will result in overheating of the tube and also the ligament causing cracking. This, of course, is downtime and needless expense. And there's that very important area of refractory condition. Is it severely compromised as shown here? But I do want to caution that cracks in castable material, which are 1/8 of an inch or less, will seal on their own. But something like this needs immediate attention, or very expensive repair and downtime is just around the corner. Or what about the refractory on the furnace floor in a water tube boiler? This is here for a reason, to keep the intense radiant heat off the lower drum or drums. If this is compromised, it needs to be repaired, or steam blanketing of the drum might occur, leading to circulation problems and possible boiler downtime because of pressure vessel failure. And then there's the all-important throat tile. This not only insulates the steel burner housing, it also assists in combustion and shaping of the flame. You see any large cracks or pieces broken off? If so, these pieces need to be patched or replaced. And the same with the furnace liner surrounding the front portion of the furnace in a Firetube boiler. Any large cracks or broken pieces need to be fixed. Now, once the pressure vessel is inspected and or repaired, including all the refractories, it's a thumbs up to move to the exterior of the boiler, and let's check the important burner components. And we'll start with the burner's combustion control system. Is it a single point linkage system as I'm showing you here? If so, turn on the power and place the programmer or the run test switch into the run test switch mode, allowing you to manually drive the air damper from low to high fire. Now, does the linkage move smoothly or does it hitch and slip? If so, adjustments and or part replacements may be in order, as this will affect the efficient and safe fuel-air ratio that you're trying to accommodate as this burner modulates from low to high fire. Or if your boiler does modulate a lot during the course of a day and the existing linkage needs attention, that single point positioning system, now is probably a good time to replace this linkage system with a parallel positioning one, as I'm showing you here. These independent actuators controlling fuel and air through a central control will hold much tighter tolerances while precisely repeating this action as the burner modulates, no matter how often. And this certainly saves energy. And finally, make sure you consider the age and the feature set included with your burner management system, or as we refer to it as a programmer. Is it outdated? The new ones today are microprocessor based and include not only the sequencing and safety features, but an array of callouts, an array of alarms and fault indicators, which assist greatly in cutting down on needless service calls and costly boiler outages. So, enough on the boiler walk around and the things you need to pay close attention to in order to avoid needless energy waste and, of course, costly downtime. Let's now turn our attention to the heart of the program today, the boiler safeties, their function, and how you set and then you check them. On the screen now are the safeties we are going to be discussing today, and I'm going to review them in the same sequence that your burner management system does. The ones I have highlighted in red are what we refer to as running interlocks, meaning during any point in the burner's operation, if one of these fails, the switch opens, the burner will shut down after going through a post-purge. The other two on top, the gas valve proving switch on the gas valve or valves, assures that the valve is closed before trial for ignition. If the switch is not made, the burner won't start. The same with the oil gun switch. If burning oil, it needs to be closed with the oil gun in position or the burner will not start. I also wanted to show you a very popular gas train assembly often used today, a unitized or a modular system incorporating dual gas valves, a vent valve, high and low gas pressure switches, and a pressure sensor for valve tightness checking. With this system, the upstream valve, number 1, is closed before trial for ignition. If no pressure is sensed between valves number 1 and 2, well, we know that it's holding tight. After proving this, valve number 1 opens, and if pressure builds, well, we now know that valve number 2 is holding and is tightly closed as well. All of this is to ensure no gas leaks into the furnace after pre-purge, causing an uncontrolled and unsafe light-off. Next, we want to check the operation of our operating controls. And as you can see, we have 3. The operating control on the left, the high limit control, and the modulating control. As noted on the slide, the operating control is responsible for turning the burner on and off based on the desired pressure or temperature that the system is calling for. It also uses a subtractive differential setting, which is the point where the burner cycles back on after being turned off at the operating set point. Here, let me show you a little bit more closely what I mean, because this gets confusing at times. Let's say that we want to maintain close to 100 pounds in our system. This is where the operating control is set. Note the arrow on the right coinciding with the scale on the controls right. Then on the left, we have the differential setting, which is subtractive from the set point. Meaning in this example, if we set the differential at 5 pounds, the burner comes back on at 95. Now, important thing here is to check these settings against the boiler's pressure gauge when the boiler is operating to make sure the settings are accurate. And if not, the control may need to be changed out, or your pressure gauge may need to be recalibrated or changed out. The safety we have for controlling overpressure is the high limit control. This, as you can see, is set above the operating limit setting and has a fixed differential, so its switch is always closed unless the set point is reached and breaks power to the control circuit, shutting off power to the burner in the case of a high pressure occurrence or a failure of the operating control. Testing this switch is done according to the notations on the slide. Make note first of the current setting. Reset the control to below the operating limit control. The burner should shut off. And if not, We have to go through the checks, find out what is wrong, probably replace the control, obviously, and then if it's fine, return the control to its current setting and then continue. Testing this switch is done according to the notation. Oh, I'm sorry. I already went through that. The next switch that we want to review is the combustion air proving switch. This is the device which assures us the combustion air fan is powered and delivering sufficient air for good combustion. Now, as you can see with this gun burner, it is located in the air plenum just before the burner's blast tube. And the switch mechanism is normally open, and it will close on a pressure increase within the air plenum itself as the burner will cycle through its pre-purge and then continues as long as the fan is running. Removing the switch cover reveals the dial which, for setting and checking purposes, the burner management system is placed again in the run test position, and the burner's damper is driven to the high fire or fully open position. This is the lowest pressure one would expect while operating automatically. Now turn the burner switch off and set the switch to the lowest setting and see if the blower starts after turning the burner switch back on. If it does, the combustion air proving switch is defective and needs to be replaced. And finally, return the dial to its original setting or slightly above the lowest setting so the switch makes when the fan is again powered, allowing the burner to sequence and proceed. Next, we're going to check the low gas pressure switch. This switch is there to assure the correct amount of gas is being furnished to the burner to allow full input, and also to assure proper velocity through the burner orifices to allow proper mixing. Low velocity can cause raw gas to pocket and not properly mix and result in rough or very dangerous reignitions. The control is normally set at slightly lower a pressure than the normal operating pressure, but never less than 50% of the rated downstream pressure from the main gas pressure regulator. Now, being a normally closed switch, it opens as a result of low gas pressure, breaking power to the gas valve while providing power to the vent valve in a double block and bleed arrangement, as I'm showing you now on the screen. So to check the operation of this switch, close the manual gas cock and start the burner sequence. If the burner advances through its sequence, the trial for ignition, the switch is faulty and it needs to be replaced. Then after determining proper operating status, return the manual gas valve to its open position and then reset the manual switch on the device. The high gas pressure switch, noted as HGPS on the screen, is located, as you can see, downstream from the gas valve, or valves, and is there to assure the burner is not overfiring and creating a dangerous fuel-rich condition. This switch operates just the opposite of the low gas pressure switch. It opens on a pressure rise above its operating set point, which is above the low gas pressure setting and above the normal operating gas pressure when full input is achieved. To check this switch, remove the cover and note the operating set point. Now dial it back slightly while the burner is powered and see if the burner shuts down. If not, kill power to the burner and replace the switch. If it does work properly, of course, then return the switch to its proper operating set point and proceed with further safety checks, which in our program today will include the low oil pressure switch, assuming we have light oil as either a primary or a standby fuel. This switch is there to assure we have sufficient pressure to make input and also atomize the fuel to prevent oil pooling and poor mixing from the nozzle, and again, rough lights similar to a low gas pressure situation. One of the differences, I might add, with the low oil pressure switch versus the low gas pressure switch is the low gas pressure switch needs to be manually reset upon a trip, where normally the low oil pressure switch is a recycle limit, meaning once the pressure returns, it will allow the burner to start in sequence automatically. To check the operation of the switch, and there are various types, I might add, remove the cover and notice you have a normal operating set point with a subtractive differential, similar to the operating pressure control. And this differential is normally set about 10 pounds. Reduce this differential to almost 0 and start the burner sequence. You should experience a lockout. If not, again, the switch is probably defective and should be replaced. The complement to the low oil pressure switch is the high oil pressure switch, which works similar to the high gas pressure switch, with a setting above the normal operating pressure, which then assures the burner is not receiving excessive oil, which is not properly mixed with combustion air, causing excessive pooling and sooting and possible fireside explosions. It is easily checked by removing the switch cover and noting the set pressure, dial it back, and start the burner sequence. If no lockout, the switch is probably bad and should be replaced. The last switch we'll be reviewing today with regard to light oil firing is the atomizing air proving switch, which many burner designs out there today use by incorporating compressed air either from the plant or from an integral compressor. It's employed to more fully atomize the oil for a cleaner burn, supplementing the pressurized mechanical atomization. When this is the case and air atomization is employed, a low oil atomizing air proving switch is normally included to assure complete atomization. If this is not the case and the atomizing air is too low, pooling of oil and coking of the nozzle can result, which not only can pose a dangerous fireside occurrence possibility, but a maintenance headache as well. This switch is set during the pre-purge cycle within the burner management system, and we place it in the run test position again, and the main combustion air fan and oil pump will be running. Set it slightly below the optimum running pressure and not too low to cause nuisance shutdowns. To check the switch, note the pressure setting and dial it back a bit. And if you do achieve the lockout, or don't achieve the lockout, you've got to replace that switch. The next to last safety device we'll be covering today are the main and auxiliary low water cutoffs. It's what I at least consider to be the most important safety devices on the boiler, as they are the ones which prevent the catastrophic, I should say, waterside explosions that I showed you in the beginning of this program. If they are not operating properly, controlling feed water introduction and low water conditions, havoc will ensue, as you saw through the American Society of Power Engineers recap that I just showed you. As mentioned, the primary low water cutoff is also the feed water pump control device, triggering water to enter the boiler at the proper point, energizing a feed water valve or the on-off pump. As noted, it's extremely important that the switch housing, either mechanical switch or mercury types, with the connected wiring and switching, they be in excellent, pristine shape and certainly absent of any tampering. We need to make sure the gauge glass is aligned and not scaled. It's not cloudy or worn or etched. And then the cross-connecting piping is clean. Not like what you see here, which is exactly the condition that were the conditions which precipitated that border launch in Tennessee that I just showed you. A lack of understanding regarding the function of the low water cutoff and the need for its proper maintenance and care. Care like routinely blowing the device down on a daily or a shift change basis, and then at least every 6 months or more frequently, load conditions allowing, conduct an evaporation test to make sure the low water cutoff is working as it should. To do this, secure the feed water supply, shut it off, and allow the boiler to naturally steam or evaporate off. Then watch the gauge glass closely and make sure the burner shuts off at the low water point in the gauge glass. If not, shut the burner down immediately, allowing the unit to go through its post-purge and then off. The boiler should not be started again until the cause of that failure is determined and then a remedy is applied. The same with the auxiliary low water cutoff. It too could be looking like this if proper maintenance is not carried out. To check it, apply a jumper wire across the low water cutoff switch to allow for the evaporation to occur down to its low water cutoff point. And this jumper wire should be very long so it's not left in there. Make sure of that. Once this test is concluded, that jumper wire is removed. If the auxiliary low water cutoff is on the opposite side of the boiler and does not have a gauge glass, which many don't, and they do normally are mounted on the opposite side, you'll be watching the gauge glass on the primary low water cutoff, and once the water disappears from the glass, the auxiliary low water cutoff should trip, shutting the burner off. If not, the boiler should be secured and the problem remedied. Procrastination is certainly not an issue in this case. The last safety device we'll be reviewing today is the flame scanner, which proves and supervises both the pilot and the main flames. Now, what we're looking for here is the condition of the cable and the scanner eye, making sure it's not sooted or it's not cloudy, certainly not cracked. To check its operation, and with the burner running, pull the scanner and see if the burner locks out on flame failure within 1 to 3 seconds. If not, secure the boiler and replace the scanner, or have a qualified technician check it out for proper placement and alignment before the boiler is put online again. So that's our program today, covering some of the key expendable component parts on a boiler which impact reliability and operation, and certainly the operational cost, and of course the safety devices, which need to be routinely checked to assure they're in proper working order, keeping personnel and the facility free from what could be, and as what I showed you, catastrophic losses. So here are what I consider to be the takeaways today. Boiler occurrences can be classified under these two headings, Fireside and Waterside. Safety, knowledge, training, and proper operating procedures, that's what you have to apply to keep the boiler plant, the boiler, all the people around it, and within the building safe. Training programs are available, including tailored on-site programs at your facility. Boiler downtime. Check Fireside and Waterside based on previous notations. That's how you circumvent that. Saves energy and, of course, costly downtime, as I mentioned. It's not just the downtime, but it also could be product loss as well. Regularly check the boiler safeties using the burner management sequence, burner management system sequence cycle. You'll start off with pre-ignition, your pre-ignition checks, of course, and then, of course, you're running interlocks that I just went through with you. Low water cutoff is key. Make sure that that's properly blown down, that the gauge glasses are aligned, that you've got the proper settings, or that you've got the indicators on that gauge glass as to where the low water cutoff point is. Then, of course, the routine maintenance that I just went through. And then the evaporation check. I can't emphasize this any more emphatically. That's the best way to check these low water cutoff devices, is through evaporation. Otherwise, when you're just blowing it down and then the burner trips off, you've got a large differential there between the pressure on the water side of that low water cutoff and then the atmosphere in the open drain valve where you're going to atmosphere. That can force that float down into some sludge and give you a false indication that the bowl of that low water cutoff is actually clean. Evaporation test is the way to really check these devices. All right. I think it's now time, Susan, to give us your feedback on some of the questions that you've received. And I've got Ron here with me, and we'll do the best we can to answer those questions.